before we send this out. That said, we're going to cover the couple major topics in for this exam today, and that will be like architecture, microarchitecture, caching, memory, and virtual memory. Does anybody have a preference of how we start? What are y'all most confused about?
Virtual memory.
Virtual memory. All right, Shrag, you want to talk about virtual memory?
Sure.
All right, Shrag is going to talk about virtual memory.
I was thinking it'll be mostly like Q&A based, but we can go over like a conceptual review as well. So who would prefer that? Okay, good enough. Let's do that then. Okay, so virtual memory. Okay, the concept behind virtual memory. Well, there's a few. I guess I'll motivate it a little bit first. We have like in a modern computer, we have like hundreds of processes running. If you ever open up Task Manager, Windows, or like HTOP or whatever in Unix, you'll see like a bunch of processes. You don't know what they are in a lot of cases, but they all are like doing some useful work. And the processor, assuming there's just a single core on the processor, which is not true anymore, but the processor is going and like giving you the impression of doing running multiple processes at the same time. But really, it's just doing it sequentially, and it switches so quickly that it looks like it's going simultaneously. So, because of that, each of these processes, there's a few issues that arise. One of them is how do you manage how much memory each process gets? You can do that ahead of time. Maybe someone's writing a program that they say, okay, we'll give it 4 megabytes and it'll never need more. Or maybe there's a program the OS might need 8 gigabytes. Shouldn't be the case, but there's different, I guess, upper bounds on how much a program will take. And then you could allocate memory. Say like you have 16 gigs of RAM. You could say, okay, I'll give this process a fixed 4 megabytes. I'll give this process a fixed 8 gigabytes. And that has a problem where basically, what if a process needs more? Or what if it's not using all the memory that's been allocated? Then it's just sitting there wasted. So one advantage of virtual memory is you get basically the process gets to use as much memory as it needs, and the OS goes and manages and says, if you're using too much and I don't have enough RAM, maybe I'll kill you, maybe I can't launch another program. There's a lot of advantages that you get if it's managed in the OS. So virtual memory is a means of doing that, and that particular aspect of it is kind of, you can think of it like process isolation. Each process has an appearance of some amount of memory, and whether it uses it or not doesn't make a difference to the process, but it does make a difference in the OS. The OS is going to go and manage, let's say a process requests initially 8 megabytes of stack space, but it only uses like a megabyte. Well, it'll never even allocate the rest of the space that it needs. So that's one advantage of virtual memory. Another problem that arises with multi-programming is running multiple processes. What if one thing is like, let's say your web browser, and you have like, you're sending like bank information, you're logging into your bank account. Another process on your computer is running, and you somehow got like malware. That process should not be able to see what's going on in the browser. And if it does, it could figure out potentially your password and all that. And so you want some sort of security aspect of it. You want to make sure one process is isolated from another one in terms of both its memory space and also like the permissions. You don't want to just like willy-nilly, some guy goes and reads location 10,000 and it just happens to be like the most important part of the OS and like destroys it. You don't want that to be the case. So virtual memory is solving both of those things. And that's kind of conceptually, like, not really conceptually, that's what the purpose is. The way we implement virtual memory, are there any questions on that? Okay. Okay. So the two terms, I'll write them down. Well, that's good. Okay, process isolation and protection, permissions, are the two things. So process isolation, sorry. address translation. And what? Demand page. Okay. 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 Sure. Address translation, demand paging. Address translation is basically the aspect where each process has the appearance of its own virtual memory, and so the appearance of its own memory, and there's a process in the OS that's handled where it basically takes the address that the process sees and turns it into a physical address. Demand paging includes basically writing to disk. It's kind of an umbrella term for like writing to disk, the paging, where you, if it doesn't fit in memory, you can write to disk, and it also takes care of permissions and stuff. So those are the two terms. Oh, this is okay. Sorry, I must have forgotten that. Okay. So, all right. One more time. Sorry. Address translation has a translation process and also keeps track of protection. Demand paging is the illusion of a big memory space when you may not have that much physical RAM. So those are two terms with
Can you have one, not another?
another one.
Without demand paging, we have other translation. Like
Yes, you can. It's a good question. So he asked if you can have one without the other. You can have address translation without demand paging. And the problem with that is demand paging is like kind of important because you need to be able to like if your process requires a lot of memory and you don't have that much, then you can go write it to disk, but you don't necessarily need to have that. It's more like if you don't have the same memory space. Whereas address translation is you can have demand paging if you don't do address translation because I guess you still need some aspect of translation. Because if you have like the appearance of a huge space, but it maps directly to the physical addresses, let's say you have extra space in your virtual space, then you wouldn't be able to do a direct mapping. So there's still some level of translation. But yeah, those are the two terms. So virtual memory, the implementation. I won't go into like all the motivation, all the attempts that have been made. But what we have now is basically we split up the virtual address space and physical space into pages. And pages are a fixed size of 4K usually. It doesn't have to be 4K. But it looks something like this. You have a virtual address space. And then you have several pages in there. Then physical address space, which is usually smaller. Does not necessarily have to be smaller. But one of these guys maps directly into one of these. And so just to note on terminology, when it's in the virtual address space, it's called a page. When it's in the physical address space, it's a frame. So you can think of the physical address space is broken down into frames, and the OS will insert pages into those frames. So initially, let's say the physical address space doesn't have anything, and the OS is launching a new process. Then it'll take this page, for instance, if this is where the code is, and pick a frame that's open in physical memory and map that. And so when you access this virtual address space in that program, then it'll map to this physical address, and the OS is taking care of that translation. So really in between here, you have a virtual address, which the process knows is this box called translation. And out of the translation box comes a physical address. And this translation is kind of the core implementation of what virtual memory is, what we've discussed. So are there any questions so far?
this box in the CPU.
This is managed by the OS. The translation is managed by the OS with some support in the microarchitecture. The architecture can do the translation, but the OS kind of manages how where the things go. And you'll actually see this in Lab 4, which I think is Lab 5. Yeah, Lab 5 version 1. So you'll do like a translation like this, and there is some part of it that's done in the microarchitecture, but it's kind of managed by the OS. Okay, so virtual address, translation, physical address. And we decided, after some experimentation in the past, we've tried different things. We found paging works really well. So we have, we break down these virtual address space into pages, have physical frames of the same size, and you map pages into those frames. And so now, going back to our two aspects of virtual address, virtual memory, we have address translation, which we've shown that we have this page, it goes to a frame, and you need a translation process. So let's say you access byte 3 of this, that it goes to byte 3 of the correct frame. So that's your address translation. Demand paging is handled more by the OS, and it says, let's say your virtual address space is huge, and the process is using a lot of it, but your physical address space is small. Well, the OS is going to keep track of that and say, like, it'll have some replacement policy, say we'll keep some of it in physical memory, and the rest of it will have to go on disk, because we're still using it, but we don't have the actual physical RAM for it. And just another term, the amount of space you're using in your virtual address space that a process is using is called the working set. So the working set is basically just a term that says you're using these pages of your virtual space. Yeah.
Is that overall or just things in physical memory at the time? So everything that your program's using or could be using?
I believe it's in the virtual space, so it could be on the disk. Yeah, but then the working set, the pages in the virtual space you use. Okay. So we've gotten with our pages, we've gotten address translation, demand paging, and then we have to do this translation step. So translation can be done in a bunch of ways. Let's say you have a virtual address, and we have 4 kilobyte pages. That means you have, and let's say it's byte addressable. So you have 12 bits for your offset, and then however many bits you need for the virtual page. The 12-bit offset, this is basically when you get a page, you get like basically the base address of the page, and you can go and offset up to 12 bits, so up to 4,000 bytes in there, and this is what selects the byte that you're actually reading. And then whatever is here is going to tell you which virtual page. So let's say, for example, these are 32-bit addresses. So if the whole thing's 32 bits, that'll be 20 bits for the virtual page number. Okay. 20 bits for the virtual page number. What that means is basically this virtual space right here, you have, from top to bottom, you have 2 to the 32 bytes in a byte addressable 32-bit address machine. What that doesn't tell you is how big your physical memory is. Your physical memory, in theory, could just contain a single frame, in which case your entire physical address will just be the offset. Or it could be the same size as the virtual space, or it could be smaller, it could be bigger. The physical address space is basically independent of your virtual address, the size of your virtual address. And so what you also need to know is how big your physical address is. And let's say we have 16-bit physical address. So we still have 12 bits for offset. And that's the case because once we get a frame in physical memory, we want to make sure that the offset in our virtual page is the same as the offset in the frame. Because you're getting both of these in this case are 4 KB, and so if you access like the 10th byte of this 4 KB chunk in virtual memory, you want to also access the 10th byte in the physical memory. The only thing you're really doing is finding out where the offset is in physical memory. So the offset, bits of offset is going to be the same. We have a 16-bit address. So in this case, we'll just have 4 bits for the frame number. Physical frame. And these are our two addresses. This is just in this situation. You can have different sizes of both of these. Okay, so now we have the translation step. We've already established that the offset just gets mapped directly. What we need to do is keep track of basically these 20 bits, what 4 bits they map to. And if in the OS, you also have to keep track of if we're using more than 16 pages of virtual memory, we have to keep track of where they are on disk. That's something that you don't really need to concern yourself in with this class, but it's something you should be aware of. The OS does manage like where it's located on the disk, but the virtual, like the actual translation, is what we'll talk about. So we need 20 bits turned into 4 bits, and the way we do that is keeping track of something called a page table. Page table, you can think of it just like a consecutive chunk of memory, and we'll say this is the base. So that's your base. You need to map these 20 bits to the 4 bits. So how many entries do you need in this table? To the 20. Yeah. So you input in 2 to the 20 bits, and you output 4 bits essentially, which tells you this. There's other information in here, but among other things, you're doing the translation step, which is 2 to the 20. So you have to make sure you account for every possible possibility of the virtual page number, and you have to be able to store which frame that's in. So this is 2 to the 20 entries high. 2 to the 20 entries, and we call them page table entries. So each virtual page corresponds, or shouldn't say correspond, it's associated with a page table entry. And the page table entry tells you where it is in physical memory, or if it's not in physical memory. And that implies, in one of these page table entries, we'll need at least, abbreviated PTE, we'll at least need a valid bit, and a PFN, page frame number, which this is the frame that it's mapping to, and this says whether it's valid or not. Okay, so has everyone following so far? Yeah. PTE is page table entry, PFN is page frame number. We have at least this information. Oh, yeah.
So the PFN is 4-bit in this case. Right?
Yes, yeah, good point. So the PFN is 4 bits in this case, because it just needs to map to a 4-bit frame number.
So every time we've gone over the page table entry, there was no mention of how it knows whether or not it's on disk or in RAM. Do we need to worry about that?
You don't need to worry about that. That's managed by the OS. Actually, in something called a secondary page table, you do not need to know about that. Just assume if it's invalid, then it's on disk. And there's also like demand paging. We mentioned like one of the aspects of demand paging is that if you're not using, this isn't necessarily true, but if you're not using, if you never use like a page in your virtual space, it may never even create that page. Because you're sure you have all this stuff, but like you still want to store 2 to the 20 pages on disk if you're only using like 1,000 of them. Right, so that's also another aspect of demand paging that's also handled by the OS. You don't need to really know the details of that. Yeah. It's the same kind of, conceptually it's the same. The terminology is used with, pages is with virtual address space, frames is with physical address space. So, they are the same size. And the frame is basically, you can think of it like a container, and the OS goes and puts a page inside that frame. And then the frame is like, it's a container, so you can put any page in there. And the OS is managing which page goes into which frame. But they are the same size. So conceptually, you're just breaking down your address space into these pages or frames. They're both the same size, but it's just whether it's on the virtual address space or the physical address space. That's the distinction. Okay, any other questions? Okay. We have our page table with 2 to the 20 entries, 2 to the 20 PTEs, and we say that it has a valid bit and a PFN, page frame number, in here. And it has a little bit of more information. Like when we discussed with caching, the tags need to have like, or the extra metadata needs to have your tag, needs to have your your valid bit, and a little bit of other information. So this is somewhat similar. It's doing a translation, so it's not quite the same, but you still need similar sort of information. For example, you only have these 16 frames of physical address space, and so you'll need to manage somehow which frames do I replace if I need to bring in a new page. So you have some replacement bits, and also let's say you write to one of these frames in physical memory, then another page is coming in and says it wants that frame. Well, you need to make sure that you also keep track of whether it's dirty or modified. And then we've also discussed one of the aspects of virtual memory is protection. So we haven't discussed in too much depth, but you also have some sort of protection bits. And this is generally true, but you don't have to have protection, for instance. You don't have to have a dirty bit. You could always just write the page to disk. So there's optimizations you can make, but this is generally what you'll see in a page table entry. Okay, so we have this, and this system works. We'll get a virtual address space. We'll get a virtual address. Look it up in this page table, where the page table is sitting in memory somewhere with this base address. And all you're doing really is taking this virtual page number, finding the offset in here, getting that PTE. Then from the PTE, you can determine if it's in physical memory or not, and if it is, you can determine where. So you can do the whole translation with this information. Yeah.
How does replacement differ from dirty?
Replacement. This refers to the replacement policy. This is whether the page has been modified or not. The replacement policy could be like LRU across all the frames in your physical space.
So you can dynamically choose which replacement policy?
No,
Oh.
it's just like in caches, for instance, if you have
that's-
perfect LRU, you need to keep track of some bits.
That would be like more than one bit.
It could be more than one, yeah. But it depends on your replacement policy. And dirty just means you've written to the page. So it needs to write it back to disk. If you're just reading from disk, reading those values, and then you're evicting it from your physical space, then you don't need to write back to disk because you never made any changes from what was on disk. Okay. Okay, so this is one aspect of it. We've gotten our translation. Another thing another advantage is you can have multiple processes.
Can you slide it down a little? Thank you.
Virtual address space 1, virtual address space 2, and we still only have one physical address space. Okay? So we said, using the same numbers, there's 2 to the 20 pages in virtual memory, 2 to the 4 frames in physical memory. And we said we can translate between one and the other. Now the problem is, we have this page table. It has your base and your page table. And you have 2 to the 20 entries for a virtual address space. And we said you calculate this by taking your virtual address, finding that virtual address page number, indexing into this table, and then getting the physical address out. Well, now we have 2 virtual address spaces. So, for this guy, if we access address 0, the virtual page number is going to be 0. Similarly, for this one, if you're accessing address 0, then you'll be getting virtual page number 0. So both of these could be addressing location 0, and they both have the same virtual page number, but you need to somehow map them to different pages, different frames of physical memory. What that implies is there's not just one page table, there's actually one page table per process. So as if 2 to the 20 entries wasn't enough for the page table, we also have essentially one per process. Page table 2, page table 1, we have another base pointer. And then each of these contains which frame numbers that these pages correspond to. So as you can see, this is getting pretty expensive. 2 to the 20, let's take a look at our PTE. We have 1 bit here, let's say 1 bit for replacement, 1 bit for dirty, so that's 3 bits. Page frame number is 4 bits, and then we have, let's say, 1 bit for protection. So that's 8 bytes. That means per process, you have 2 to the 20 of these entries, which means you have a megabyte of memory per process. That's not horrible, but keep in mind this has to be saved in physical memory. So that's not horrible, but let's say now you have a 64-bit address space, or even 48 bits. Right, now if you still have a 12, if you have 12 bits for offset, now we have 36 bits for page number, which means we need 2 to the 36th entries in here, which is 64 gigabytes per process. And that's a problem. I don't know about you, but I don't have 64 gigabytes on my computer total. So we need some way of managing that. And that's when we go into multi-level page tables. So is everyone clear on this before we move on? Okay, so this is the problem, and essentially what our solution is, we have all these page tables. Why not put the page tables in virtual memory as well? So you always need something in physical memory to keep track of like where these mappings are. But just roughly, we'll have like what we call a page directory. And the page directory, instead of giving you a page frame number for actual data, it gives you a page frame number for a page of page tables. So I'll draw that out. It's a little bit difficult to digest. So this has a PFN in here. And that'll give you a base address. And usually what we do is we take the offset from our address and just index into this and get our data. Well, now we actually have a second level of translation where this will give you a page frame number, and then you'll use another index to offset into here. And let's see, use this one. That'll give you another page frame number, and that'll give you the base address for your data, which you can then access. So we haven't discussed too much in depth. The only mechanism we've talked about with multi-level page tables is x86. And I'm sure you all have, if you looked at the practice exam, you've seen lots of VAX questions. So I'll reiterate this. There's no VAX on the exam. We haven't covered VAX, and there's no VAX at all. So if you see a VAX question, like, you can just very comfortably skip over it. x86, basically, I'll go back to our 32-bit address space. We still have 12 bits for offset. But I mentioned now we have an offset into our second level page table. So I'll use the terms page table and page directory. You have an offset into the page directory, and then an offset into the page table. And so we split our virtual page number into 2 parts. And this is your page directory offset. And this is your page table offset. So this is going to index into here. Then this comes out. And you do a plus with this basically. And that gives you another index. So essentially all you're doing, you're just adding this offset to this base register for this frame. It's the base value for the frame. And then you use this thing. Similarly, you have an adder here. And then you just add this offset and get your actual data. We'll draw this a little bit more clearly. But this is a general idea. The advantage of doing this is now this page table can just be somewhere in virtual memory because it can be indicated whether that page table is valid or not. And very conveniently, with x86, these page table entries happen to be 4 bytes. Ours is 1 byte. With x86, it happens to be 4 bytes. And we have 10 bits here and 10 bits here, which means you have 2 to the 10th. You have 2 to the 10th page directory entries, each of which is 4 bytes. That ends up being 4 kilobytes, which is 1 page. And this also happens to be 10 bits. You have 2 to the 10th page table entries, and that also fits in a page. And so essentially we've taken our page table, instead of being like gigabytes of memory, we fit them into pages, individual pages, and we can say those can also be in disk. So I want to emphasize, like, we haven't really covered this very much in depth. I just wanted to show the solution for like the problem of having that much space. You need to know maybe the basics of this, but this isn't going to be heavily tested on the exam.
You say you put the virtual address?
This is a virtual address. Yeah. Previously we had a VPN and then an offset. So now our VPN is kind of in 2 parts. That's really the only difference. And you have 2 levels. The first part is indexing into the first table directory. Second offset is indexing into the page table. Yeah.
Can the total amount of virtual address space be larger than the amount of space on the disk?
Yes. And that can only be possible if you have that aspect of demand paging, where if a virtual page isn't used, you never even it's just nowhere. It's just gone. And that's fine because if you're not using it, then who cares where it is? But if you're using a virtual address space and you're using everything in there that's bigger than the disk, then you'll start running into huge problems. And in fact, usually you can't just use the whole disk. There's a space allocated on your disk for how much you can fit this.
User allocated.
Yeah. Okay. So any questions about this? This is conceptually all you should need to know for the exam. Yeah.
In actual x86, I remember there being some sort of shifting that we had with the addresses and the page directory and page table.
Yes, and that's correct. Basically, I said the page table entries are 4 bytes instead of 2 bytes. Sorry, 1 byte. And so when you get this offset, you need to shift by 2 before you add it to the base register. And really all you're doing is you're just saying times 4 because each entry is 4 bytes. So if you access entry 0, it's at location 0. If you access entry 1, it's at location 4. So you just shift it by 2. Okay, any other questions? Okay. This is the kind of working time. Here's the second. Okay, so we had a kind of conceptual virtual memory problem. Okay.
So the shift is just for the page drag and read and page table, not for the
What was your question, sir?
I saw the shift part only for the
Yeah.
page table there.
Yeah, that's also correct because we actually have 12 bits here. We have a byte addressable memory, which means this is in bytes. And so if it's in bytes, you just if you're accessing byte 1, it's at location 1 or offset 1. If you're accessing byte 10, it's at offset 10. So you don't need to do the shift because it's already on that granularity. Okay. Yeah. Okay. We have a question. Okay. Part B. A cache takes an input as an address and returns data. If the data at the address is in the cache, if the data the address is in the cache. A TLB is just a cache. So we've mentioned TLBs. What is the address used in a TLB and what data is returned? So TLB, it stands for Translation Loci Buffer. And we've also mentioned it's basically a cache that's used to help us with translation in virtual memory. So I guess it's not on anymore. But when we were doing the two-level translation, for instance, and this problem happens with one-level translation as well, you need to access memory to get your page table entry out. So the page table entry is sitting in memory somewhere, and you need to actually read that memory, right? So to do an access for, let's say, 1 byte, first you have to read the page table entry so you can do the translation, and then you go and read the actual byte you want. So there's that implicit memory read. And even furthermore, when you have multi-level, you need 1 read per level. So x86 two-level translation, you needed to read first the page directory to get that page directory entry. Then you get a page table, and then from the page table, you do another read to get your page table entry, and then you can finally go and read your data. So TLB is trying to help you overcome having to do all those reads. And essentially, it's a cache. So with that information, what do you think the TLB contains? Page table entries. I don't know if you get that. These are page table entries. And what do you put into the TLB? Yeah, so you put in the virtual address. Is it the whole virtual address? The page number. Virtual page number. You put in the virtual page number, and out comes a page table entry. A page frame number. And so without having to access memory, you can get that page frame number with the convenience of having a cache, which is fast, and you can do the computation without accessing the inner pages. Okay. And that's for the translation part. You do need other information in there as well. Let's say you're trying to index using a virtual address, and the virtual address happens to be a system page, an OS page. So if you go to the TLB and you read the TLB, you get a frame number. Should you just be able to go and read that frame number? You need permissions. Yes, you also need to keep track of permissions in there. So you have to make sure that, first of all, that you can get the page frame number from the TLB, and then if you get the page frame number, you need to be able, you need to make sure that you're able to access it with the permissions. Okay, you want to say anything else about that? Okay, so yeah, TLB is used like a cache. We haven't really discussed the internals of the TLB, but you can picture it as just a cache, and the address input is the virtual page number. Yeah.
So, would you need some sort of identifier for the process since page numbers are unique between?
That's a very good question. Yeah. So there's a couple of ways of doing that. You may need to use a process ID. I believe what's usually done is on a context switch, when you switch to a different process, it actually just clears the TLB entirely. And that's one of the reasons context switches are considered so expensive. We'll talk a little bit more about it in the semester. There's other complications that arise. But yeah, that's a good question.
And TLB is in hardware?
Yes, TLB is like a cache. You could give her L1 cache, your L2 cache, you have a TLB and it's a cache.
TLB outputs a page table entry.
A page frame number and protection number. Yeah. You don't need the whole entry necessarily.
And maybe permissions as well.
Yeah. For instance, you don't need to know if it's dirty or not just from the TLB. Because the TLB is helping you in translation, not in eviction.
Put in a virtual address. The tag is the whole virtual address.
I mean, it depends on the structure. With the normal cache, you can have some bits for index, some bits for cache blocks, offset, some bits for your tag. And so, the address coming into the TLB is a virtual page number. And that address, you can break that virtual page number into index bits, offset bits, and tag bits, just like you would do with any other cache. Yeah.
Why is the TLB doesn't have specific offset?
Because, well, when you're doing the when you're doing the translation, basically the offset actually comes. Okay, the offset basically once you've gotten your PFN, you add the offset. So you don't need to keep track of the offset because you're adding that later on anyway. And furthermore, if you included the offset in your TLB, you'd have a lot of additional stuff in there because like you want to make sure that the same if you're accessing address 0 and address 1 and your page size is 4 kilobytes, it's the exact same frame number. So you don't need to keep track of like an entry for address 0 and address 1 separately. You just need to keep track of the virtual page number. Did that answer your question? Okay. Any other virtual memory questions? Yeah.
For x86, it would need to have these directory entries as well in the TLB.
That's also a good question. So why not just keep track of the whole translation? You put in an address and you get out this page frame number. Right? You don't need to keep track of this and then access the TLB twice. You could access it once and just get the entire correct page frame number. And while that's true, you may also have page directory entries in there. Because if you're accessing a page table, like let's say you need to change a bit in the page table entry, then you need this, like you don't care about the data, you care about this thing. And so you cache the VPN for the page table, and the output would be the PFN of the page table. So it can do both. Yeah.
Like if the data, the address is in the cache. Like the question without this sentence is easier to answer, but this one confuses me.
It's just saying, like it says the cache takes an input as an address and returns data. Well, if it doesn't have the data, it can't return the data.
What's the data type? What do you need? Which
Just
data?
a normal cache. Ignore like virtual memory, ignore all that. A normal cache, let's say you're reading a location in memory, it just returns like a byte or whatever. If you're reading a word, it will return like the word. So that's the data in that case. But if that word isn't in the cache, if you have to go to memory, then the cache can't return that word. You have to go to memory. Right? So similarly, with the TLB, you index with this virtual page number, but the TLB has like a finite size. And let's say it's the first time you're accessing this virtual page number, well, you have to go through this whole translation process to figure out exactly what the page frame number is before you can save that in the cache.
Okay, so what's gonna be sent at the BTE?
Yes.
So the data is the BTE.
In a TLB, yes. In a cache, the data is just
Yeah.
data. It's just whatever, instructions, data, whatever it is. Okay, any other questions? Okay, we're gonna move on. That took up longer than we expected. Okay. What do you guys want to do next? The main topics like physical memory,
Caching.
caching,
Caching.
microarchitecture.
What's up?
Should you use part B on two on the same test?
Maybe. Depends on what the question is.
Oh,
This was, you should be able to find this in the homework solutions.
Yeah.
Do you want to talk about it any more than that? 9?
Yeah,
Probably. Problem set 9?
Yeah.
So, I mean, we have solutions for this, so it's probably not instructive to spend time on. Don't we have
For that one, not so sure. So I couldn't really come up with it.
Do you want to see the process of how this is solved, or do you think the solution is to just
part C?
Oh no, the process for
Okay, so when in this diagram, basically the MRU and LRU designations, it's just to help you figure out what order things came into the cache. Because normally there's some like replacement bits, but here it's just marking you that the way on the left is the most recently used, the way on the right is the least recently used. That helps you determine the order of the accesses. Because you know that the access that's, if you look at set 1, both ways are valid, and because the set on the left, or sorry, the way on the left is the MRU, you know that set 1, the left entry, came in after, or it was used more recently than the one on the right entry. So it's just labeling that for you. And I believe for this problem, it determines the order between 2 misses. Does that answer your question? Do you guys want to talk about caches? No? Yes?
Memory.
Memory. Okay. I'm not a memory expert. I think Tommy is a memory expert. So, do you guys have questions about memory specifically that I can? Yes, sir.
There was that one homework where there was a lot of confusion about the difference between bank, channel, chip, and SIM. Can you just draw like a visual like hierarchy?
So, that's very easy to answer. As far as we're concerned, this is what memory looks like. So, we have this structure. It takes in a row address. It takes in a row address. And it, this may be 8 bits or something. And it outputs something in the row. And we call this structure a DRAM chip. So this is a chip. This is like actually the physical form factor of a memory. Like the black box you see on your memory sticks, that's what this is. And as far as we're concerned, the only other unit of memory so we have these things called chips. And we also have these things called banks, which in our class, this is, in our class, we're going to call banks collections of chips. So, for example, you might have 4 chips on a bank. And this means each chip is outputting 8 bits in this example. And they're all getting fed the same row address. So you can think of this conceptually as they have different parts of the row. And that means this whole bank outputs how many bits? Yeah. And that is basically it. Memory hierarchies get a lot more complicated than this. But that's what Derek wants to teach in this class, so that's all you really need.
Also, the question said minimize the box. What do they mean by the box? Like there was question.
Minimize the what?
The box. Box.
Parts.
Yeah. It was so confusing.
So that refers to
So the number
half
of the
less
chips,
chips and half less bits.
the spans too counts.
I don't remember the exact question.
It was like you get the same number of chips anyway.
Okay, that means you minimize the number of banks.
Okay, so the banks.
So that means you want a bank to be higher. I believe in that question there was like a total capacity, right, of memory.
Yeah.
And if you have the same number of chips anyways, that means you want more density on each bank. So each bank contains more memory, so you have less banks.
So they consider the bank as a part.
Yes. So more or less, you can also think of the bank as the entire DIMM. So the term DIMM actually refers to the physical form factor of the memory stick. This is dual inline memory module. So like when you buy some RAM from like Fry's, you stick it in your machine. That's called a DIMM. For our purposes, imagine that as a bank as well. And so this 32 bits that's read out of the DIMM and read out of the bank basically just gets connected to the CPU. And really, there's like a memory controller in here. But that's basically all you need to know. So Tommy made a good point that we also have these things. So these are the two like parts of memory. But then when you actually do read a memory, in a can I remove this? Are you guys still? So when we have it simplified memory question, it'll look something like that. But we also taught a bit more complicated memory, and so often when you address memory, in any actual memory, there's this thing called a row buffer, or I believe he called it a page register. So although each chip is outputting 8 bits of the total 32 bits, each row on the chip is actually bigger than 8 bits. Right? So you have, you basically concatenate each row of the chip into a larger page register, and these aren't 8 bits. These are bigger than 8 bits. So for example, if I have, let's say, 16 columns on each chip, this means that this chip reads out the row, and it'll be 18 times 8 bits. So it'll be a total of 16 bytes. And then when you address memory, you give it a row address. But you also, then usually like the following cycle, you also, or whenever the row gets read out, there's a row latency. You also give it essentially a column address. And this column address allows you to pick where in the row you want to read out. And so the column addresses all the chips simultaneously. So if you read out column 0, for example, they'll pick column 0 of all the chips. So you get 8 bits in this column, you get 8 bits in that column, you get 8 bits on that column, you get 8 bits on that column. It's all column 0. And so you read it in parallel across all the chips, and you get the 32 bits. Does that make sense? Yes, sir.
Why does the number of columns affect how wide the row is? You said that the row buffer is a concatenation of one row in every chip, right?
Yes. So when we refer to the fact that each chip reads out 8 bits, it actually is the combination of the row address and the column address that you get 8 bits from. So the way the memory is set up, you can think of the 8 bits as like a cell of memory, right? And then if you imagine the memory chip as essentially a 2D array of cells, I might have 8 bits here, 8 bits here, and so on. And so you give it a row address, and then you also give it a column address. So you apply the row address, and after the row gets read out, you apply the column address, and then you get, say, 8 bits. But when you read out the row, you might these cells are sequential, so it's usually very likely that you're going to read out the next sequential cell. So what happens is they read out the entire row address, or row that you address into a row buffer, or let me call this a page register. And so they read out the entire row and then address it here. The reason they do that is because the next time you want to read the next sequential column, if you read out the next sequential column, you no longer have to send the row address again because you already read out the row. And it's a optimization on spatial locality essentially. Does that make sense? Yeah. So I believe that's all we covered in class about memory. And simplistically, this is all you needed. makes sense? I believe we have questions on that. We do not have questions on memory right now. We'll come back to it later.
I have one question.
Yes.
So like for DRAM, you have to write back to memory so that the data doesn't, like the voltage just doesn't drop to zero, so it's still there. That page register, that you can just load one full row and then you can keep accessing that page
Yes.
register, right?
So those registers are. So I think you're referring to refresh.
Yeah, yeah.
Okay. So DRAM is generally it's called DRAM because it's dynamic RAM. The term dynamic comes from the fact that it loses its state after a certain amount of time, and this is because the capacitors essentially lose capacitance or something like that. I'm not an ICS guy. So that means at some sort of fixed cycle, this is all taken care of by your memory controller. It'll read the values out of the capacitors and write them back in, and so that essentially like recharges that those cells in memory. Your page register is generally a register, and the registers are probably something like flip-flops or SRAM, and they don't lose state, or not unless you turn off the power.
So I guess like the kind of what I was getting at then, like you know we've had questions where it's like if you access the memory you have to wait 5 cycles, basically to access it again. That's like the refresh time, kind of, or is that just that's just like the latency in memory?
So it actually just takes time to read out this row and into the row buffer. So, or sorry, I should use the terminology we call it in class, a page register. Yeah, it takes. You have to charge up the column lines, and then it reads out the bits,
Okay.
and that just takes time.
Okay, so yeah, so it's the latency of just like getting the data, not waiting for it to
Yeah.
refresh again.
Refresh. If you are refreshing, usually I believe it's on a granularity of rows in a bank. If you are refreshing those rows, you actually cannot access them at that point. Effectively, your memory controller will know that those rows are being refreshed, and they'll schedule your memory access. Yeah. So there's not that much you need to know about memory. We could stay here all day talking about
Can we talk about MSI protocol?
MSI. We're not worried about MSI. Okay. So I guess we're gonna talk about. We're gonna talk about. How about we'll talk about microarchitecture. Okay, sure. How many think we should talk about interleaving? Yeah. Okay. Can anyone tell me what interleaving memory means? What's
Means that sequential addresses lie on different chips, so that as you do sequential accesses, you can access different DRAM chips, so that you essentially master latency.
exactly? And so does that improve throughput or does that improve latency? It improves throughput. So you almost got that exactly right. Usually the term we are going for here is we interleave on banks. Because when you, as I was trying to emphasize in the previous example, when you read out, let's say 32 bits from memory, you're actually reading out 16 bits on this chip and 16 bits on that chip, if we had 2 chips on this bank. So the entire bank is busy when you're doing that memory access. So if you're interleaving, you're basically saying you have another bank. So in this case, this is 16 bits, this is 16 bits, 16 bits, this is 16 bits, for a total of 32 bits. Okay? So, depending on your access pattern, it's a very common motif. When you like write arrays in software, you won't like jump randomly around in the array most of the time. You might just read the entire array out sequentially. So that means you might want to put your every other location on a different bank. In this example, we have 2 banks, because that way when this bank is getting accessed, and let's say that takes 5 cycles, you can read off this bank. and so instead of taking 10 cycles to read out both locations, if it weren't interleaved, you only take 6 cycles because you've so let me draw. So let's do a read, and then okay. So if it takes, if we don't interleave, the next read has to come after this data comes back. But if we do interleave, since there's all this dead time between this read and this data, we can do this next read here, and then we can get the next data back here. So essentially, in this example, if memory took 5 cycles, we're saving 4 cycles. More or less.
Talking about it, are we talking about just the one request, or are we talking about the average of all the reads?
So if you're talking about overall averages, you're usually talking about average throughput. Latency refers to sending a request and getting that data
So it's
back.
one.
How long that takes. So notice here that latency has not gotten any shorter. It still takes 5 cycles from this read to this data. It takes 5 cycles from this read to this data. But we're taking advantage of the fact that the other bank is not busy on the first bank. And you can't overlap these because they share the same memory bus. If you had separate memory buses, then you could just do it completely here.
You said latency didn't change velocity.
Throughput. So you're getting 2 pieces of data in 6 cycles instead of 10 cycles, right? So effectively, your memory just got more performance, but you didn't actually improve it.
What is throughput?
Throughput is how much work I can get done in per unit time. So if I had 1 bank, I would get 1 piece of data every 5 cycles, right? If I had 1 bank. And that means I have a throughput of 1 data per 5 cycles. But since I have 2 banks, I can overlap them. This is called interleaving. I can get 2 pieces of data per 6 cycles. So that is 1/3 instead of 1/5, which is bigger, right?
Is it also possible to interleave between chips or like between memory modules, I guess?
So
Or are we only using about
for our class, we're going to have chips and we're going to have banks. There are multiple chips that are on a bank and they get read simultaneously when you do access. So that entire bank is busy when you're doing the memory access.
do you access every single chip that's within the
Yes. So that means you can't interleave across chips because when you're doing that first access, all those chips are busy. Does that make sense?
What was the benefit of using 2 16-bit chips instead of just 1 32? Was it a speed thing?
Oh. Okay, so I guess the premise that we're assuming here is that the chips, when you do one access, the chips are busy and you cannot do anything else in those 5 cycles. That is the whole basis that we're this logic depends on. And this is true of how memory works. So when we're doing, basically what I'm saying is, when you're doing this read and this data is coming back, this bank is busy. That means both chips on this bank are busy, and you cannot do anything. I'm sorry, what was your question?
What's the point of using 2 16-bit chips instead of 1 32-bit?
So, we didn't talk about DRAM design in a lot of detail, and we won't. But there's basically just layouts of memory that are more efficient. For example, we talked about if you have 16 bits in your address, for example, in LC3, it might be a good idea to have a square DRAM chip where you're addressing 8 bits on the row and 8 bits on the column. The reason being is you don't use those 2 address. You don't send a row address and you don't send a column address at the same time. So that means you can repurpose your 8 bits of address. Right? That's really all you have to be concerned with. There are sometimes more efficient ways to structure memory. And this is not a memory design class.
So
So generally, bandwidth is like theoretical throughput. Like it changes depending on what you're looking at. But technically, if you have a 16-bit memory bus, your bandwidth is 16 bits per cycle. But that doesn't mean you can utilize 16 bits. For example, memory is refreshing sometimes, and it might be the case that like there's just no way to read out anything during a cycle. That means your throughput goes down, but your bandwidth, which is your theoretical maximum throughput, does not go down because your bandwidth is just a property of the hardware itself.
Okay, so
Like you can have a gigabit connection in your house on LAN, but you might not be able to actually push a gigabit of data from a computer device.
right. So by interleaving, so you always improve throughput,
Yes.
but
You-
not necessary for
Yes, you can't really. You don't really speak of improving bandwidth per se because the hardware is there, and
Right.
what you're trying to do is utilize it better. At least when we're talking about memory interleaving.
So as long as the hardware remains the same, we cannot improve the bandwidth as such. So I remember reading somewhere the professor talking about increasing bandwidth.
So, I mean, there are ways to increase bandwidth, and we can add more. For example, we can add more memory lanes on the memory bus, and that will increase their bandwidth. And these terms are kind of amorphous because it also depends on who you ask. Because if you're doing like the actual metal layout, their terms of throughput and bandwidth are different because they aren't thinking of things at the data transfer. Right? It just depends on the context of the question.
For this class, bandwidth means the number of
Yeah, it's theoretically how much data you could get from one place to another. And throughput is based on your timing parameters and such, how much you can actually get through.
So let's say if I have 4 bands, then I can increase my throughput, but my bandwidth would still be the same because my data cost is.
Yes.
Should we always assume that we can read and ask for data at the same time?
Sorry.
Sorry, we can receive data and ask for it at the same time.
So generally, like I drew a picture here. This is referring. This top one is the address bus, and this bottom one is the data bus. And it's usually the case that these two buses are separate. But we could have a question where they're not. In which case, then no, you can't send two things on the bus at the same time. But unless otherwise stated, these two buses are probably separate, in which case you can. Oh, okay. So if you use a bus for two things at the same time, that's called multiplexing. And for example, if I send addresses on the bus as well as data on the bus, that would be time division multiplexing, where some of the time I have to be sending addresses and some other times I have to be sending data. So essentially, I cannot. My bandwidth is not as high because there's only one bus.
Right, so how is it possible to send multiple things on the bus if the bus is as wide as one address? Don't you, if you were to send like address and data at the same time, it's like
So you don't send them at the same time. You use the same wires. So that means you have to take turns, and that's what the term time division multiplexing means. You have to
so you
take
send
turns.
like 8 bits of the like say you had 16-bit addresses, you would send like 8 bits of address and 8 bits of data on the same bus.
No. So if let me extend this example. Okay, so we're doing reads, and let's say we have a lot more bits, so we can do read, right? And then now I'm doing 6 reads, so for 6 cycles I can get data back.
How can you do the last read if the data comes back on the bus?
Exactly. This is assuming we have two different buses for addresses and data. We cannot do this if we're sharing a bus. If we're sharing a bus, that means this read needs to not be done, or this data cannot be sent back Right? So when I say you're sharing the same bus, it's you have to take turns. You have to schedule it such that the addresses aren't set.
Only one cycle.
Yes.
Only one thing.
Yes. So that the time division refers to the cycle granularity. During a cycle, you either send addresses or.
So in the question asked, just mention interleaving, but I didn't mention the shared buffer. Now we can just write our assumption.
Yes, and generally, like we really haven't taught about shared buses a lot in this class. It's a pretty good assumption that they aren't. So it's a pretty good assumption that you have separate buses. So I believe all the architectures I know are separate buses. Any other questions? Sure. Problem set 8. Sharad wrote this initially. Would you like to take this? This is the one with the L2, this, and the L3.
Like in your solution, you go to the solution. Or part two, compute those cycles.
I'll be outright and say I copied the solution from previous problem set. So, let's see. For parts B and C?
Yeah.
Okay, so what was the question? Just how to compute it?
How do you get that 14 cycle? Basically, how do you compute the 12 cycles?
Okay. Well, so this part is compared to this. When we do the four-way interleaving, this part's the kind of the different thing. Because now that we have four-way interleaving, we can actually send this address. This indicates you're sending an address. This is indicating you have the data back. You can send this address while this one is working because it's like a different thing. So you can do up to 4, and then this one right here. When you go to the 5th access, or the 5th, I think you're getting words. Yeah, okay. So the 5th word that you're getting, you have to send the address after you, in the same cycle we've gotten the data back from the first one because it's going to the same bank. And so this takes 22 cycles, right here, and you get this back on the 22nd cycle. Which means you can send this on the 22nd cycle. And then that takes another 22 cycles. Sorry, that takes 21 cycles because the address and data overlap. So this is 21 cycles. That puts us at 43. Then you get 44, 45, 46. Oh, is it too small to see? Sorry. Okay. Does that answer your question? Was that, do you understand why that's the case? This is when you get your data back, and also when you get your when you send your next address. So it takes 21. On the 22nd, you're getting your data back. You're also sending an address. So that's the reason it's like a 1 here is because the 22nd part of the first access, and then the first part of the 4th access, and then it takes 20 cycles for the memory to do whatever it's doing, and then you get 4 in the next 4 cycles you get 4 words back. Okay.
So this is an example of
This is 4 banks actually. You can tell it's 4 banks because you're doing 4 accesses simultaneously, and they're both running back, and you get the results back 1 cycle apart. But then when you get to the 5th one, you have to wait for the first one because that bank is busy. And you can, I believe there's an assumption here that you can do address and data in the same cycle. Yes, there you go. So we have the shared bus thing instead of the multiplex. We have the separate bus instead of the multiplex bus. Yeah. And then C is similar. This takes 22 cycles and 23, 24, 25, 26, 29. Did I answer your question? Okay. Are you done with memory? Or no?
So we have an example memory question, but we're gonna work on it in the back for a second and come back to it later. So would you guys want to talk about data paths or caching?
Caching.
Do you want me to overview caching in general, or do you have specific questions? Okay. Okay, let's start with the general idea of caching. The caching, as Dr. Chu showed in an example, basically you have a memory where in his analogy he has an ordered stack of CDs on the shelf, right? But that's really far from the stereo, which he wants to play his actual music, right? He has to walk back and forth. So as you get lazy over time and don't organize very much, you essentially put a stash of CDs right next to the stereo. It's closer, you can swap in and out really quickly, and that stash probably contains your most commonly used or most recently used CDs, right? So basically that's the whole point of a cache. We have a cache that sits much closer to the CPU than memory does. This is because of the limitations of technology. If we could have an infinitely fast, infinitely big memory, there would be no need for caches, right? But memory takes time. Memory is a lot bigger, and so for example, nowadays it takes about like maybe hundreds of CPU cycles to read something, to read a cache line from memory, go through the entire cache hierarchy and come back, right? But your L1 cache might take maybe a cycle or two, right? So that's the entire point. As you get further away from the CPU, things get bigger, but they get slower, right? So I mentioned L1-2 cache here. It's because these days we tend to have multi-levels of caches. And so we might have a bigger cache than L1, but a slower cache than L1. Does that make sense? Right, so basically it's a spectrum, right? CPU is fast, but it can't hold a lot. You can think of registers as another level of the memory hierarchy, right? So I have registers, I have cache lines here, and then I have memory locations here. It's a lot faster on this side, but it's a lot more data capacity on that side. Right? Does everyone follow that? So how we actually implement caches. So as Dr. Chu mentioned, other architects have tried things like basically a scratch pad of data where like the programmer has to decide to write it into the scratch pad and read from the scratch pad. But that turns out to be a lot of programmer overhead, and we all know CS majors are lazy. So Shrug is a CS major. So the programmer doesn't want to do that. So why doesn't hardware do it for them? And so hardware can have good ideas of what is being used right now. It's not perfect because hardware can only predict, while the programmer might already know. But if you relieve the programmer from doing things, maybe they could be more productive on other things. So that's why we have caches. So the concept of caches is you take these memory locations and store them in your like small CD stash closer to your stereo, right? So they are the same CDs, they're the same memory locations, and they aren't addressed any differently, but they're just kept in hardware closer to the CPU for you. So in an actual cache, we have 3 dimensions. You can think of it like that. So we have these columns, which we call ways. These are usually drawn as columns. So this might be way 0. This might be way. This might be way 1. And then we might have multiple sets. Set 0. Okay. So these are 2 dimensions of caches, and we have a third dimension, which is the cache block size. So each, let me go through some terminology here. Each section of this cache, this is called a cache line. It's called a line because this is the granularity of a cache. A cache does not necessarily work on bytes. It does not necessarily work on words. It works on a unit called the cache line. This means if it goes to memory and grabs a piece of data, it's going to grab the entire line. If it puts a piece of data back in memory, it's going to put the entire line back into memory. So this is called the cache line. In this case, I'm going to draw that the cache line has 4 bytes. Right? So that's my third dimension of the cache. I have how much data is stored on a line, and that's the granularity of the cache. How many sets, which we'll talk about, which refers to how the cache is indexed, and the ways it's how if it has the same index, how many copies of, or how many different lines can you hold that index the same? Oh yes, and Tommy makes a good point. This is called a cache line. It's also called a cache block. These terms are interchangeable and exactly the same thing. A lot of people, I've heard confusion that a cache line is an entire row. This is not true. A cache line is just this block.
So line block and block size, or the line size and block size are the same?
Yes, and they both refer to how much data is on the line. Not how much like tag bits and how much valid bits. When we say line size or block size, it almost universally means how many bytes of actual data is stored. So there might be a lot of other metadata stored on this line, but the line size and the block size refers to the 4 bytes of actual data. That's from the CPU. Or sorry, from the memory. So the reason why we have these other 2 dimensions called sets and ways is because we want the cache to be fast, but also be able to store data, useful data, right? If I have a cache that's always storing the wrong data, then it's not useful, right? For example, I don't want to store any data that I used like an hour ago that I'll never touch again. So caches have to be smart about what kind of data they store. And it turns out that we could have a cache, which we call fully associative, which has no concept of indexing. So let's say I have a 4-line fully associative cache. This means that the cache, every single cache location is essentially can store any memory location. So there's no difference between storing here, 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 or here. This is fully associative. So if my cache line size is still 4, and I take my I'm going to call it physical address here, because it's usually the physical address. I take my physical address. Can someone tell me how these fields are divided up? Offset? And the rest is tag. The reason why is because there are no sets, right? Every single location can store any single other. Every single cache location can store any address in memory. And so if I don't have sets, I don't have indexes. How many bits are in the offset? I mentioned that the cache line size is 4 bits. So, yeah. So, yes, so if my cache line is 4 bytes and my machine is byte addressable, each cache line specifies 4 different bytes. That takes 2 bits. And usually on an exam, unless we write a weird problem and we explicitly state it's not a byte addressable machine, you can assume it's byte addressable. If it's unclear, and for some reason you can't ask, write the assumption. Right? Byte addressable is generally always a good assumption unless otherwise stated. Almost all machines are byte addressable. So we have a tag, and this is really nice, just having a tag and storing to any location. Because as long as we have a smart policy of how we bring in new memory location, because you can imagine this cache, 4-line cache, is going to get full. And if every single location is as good as any other location, then we can replace any single one of those locations with whatever we need from them. And if we're smart about it, we could potentially get really high performance. Does that make sense? If the hardware can somehow figure out what to keep and what to kick out, then a fully associated cache will perform very well. Like, the cache won't miss a lot. Does that make sense? But what's the cost of having a fully associated cache? Yes, you have to search it, right? So if I have 4 ways in my cache, this means that I don't know any given, like, for example, processor does a load from 0. I don't know if the load is going to be in this way, and don't know if this load is going to be in this way, or this way. I have to search all the ways. That means I need to read these 4 tags out. I need to have comparators to compare those tags. I need a huge mux to mux the data depending on which tag is right, or if none of the tags are right. And so that costs overhead. And additionally, I also need a replacement policy that can handle 4 ways. And you can imagine, Dr. Pat talked about how complicated replacement policy gets when your ways get big. So if you do perfect, at least recently used, it requires a log2 factorial number of bits. And so, like, for example, if you do 16 ways, that's completely unreasonable. Because 16 factorial is like trillions, and log2 is still like thousands of bits. Right? You just can't keep that amount of information in a cache line about replacement, right? So it's hard to have a lot of ways, but you can have some ways. And because ways have the nice property of the index is the same in this location, this location, this location, this location, as opposed to a cache without ways, you don't have to necessarily replace any given line just because another line is coming in. You get a choice in which line you replace. And if the hardware somehow is smart about which line to replace, this can perform better. All right, and we call this fully associated. So how do we address the fact that fully associated caches are expensive? Well, we can structure caches more like memories. Okay? Memories generally, you don't go into memory looking for data and say it can be in any location. You have an address of where it is in memory, right? So if we have the equivalent of a memory-like addressing scheme in a cache, we call this direct mapped. And this means that every single location has a different address. That means if my processor does a load against hex 0000, I know where it maps to in the cache. In fact, based on the scheme I'm going to talk about now, it's going to map into segment 0. And this is because in a direct map cache, there are numbers associated with each of these sets. And these sets, since there are numbers associated with these sets, you can take bits in the address and decide that those are your index bits. So this is the same address in binary form. For example, if in the previous example I have cache line block cache block size of 4 bytes and it's a byte addressable machine, these 2 bits are going to be offset. And I have 8 sets, which I'm going to pick basically some bits to represent my set. And this is often the lowest 3 bits. So this refers to these 3 bits I'm going to call my index bits. And since my index bits happen to be 0, I know that it's going to be there. So there's no more searching in this example now. Either these rest of the bits, which are the tag bits, either it's going to match this tag in set 0, or it's not. Right? There's not like 4 ways to look through. There's not 16 ways to look through. It's either going to be there or not. So that's a lot cheaper and it's faster to access the cache if you have an address. So let me go back real quick. This is called, when you address a memory and you have to compare tags of different locations to see which one it is, this is called content addressable. In which case, in this example, our tag is our content. So we need to compare this tag with the tags in the cache to see if they match, as opposed to this scheme where we just straight up index the cache. And indexing, as I mentioned, is a lot cheaper. It requires less logic, less power, and it's a lot faster in general. So the fact that these 3 bits are my index, this is called my caching function. So my caching function might not be these 3 bits. It could be the top 3 bits. It could be a combination of some logic plus some bits in the address.
So if it's fully addressable, is it always a can?
If it's so the term is fully associated.
Yeah.
But caches basically are always cans because you usually have more than one way. In addition, you have to compare tags because even if you have only one way, this location might not actually contain 0, 0, 0 just because the set number matches. You also have to compare them. And so in some sense, they're always content addressable because caches are smaller and you need to figure out if that piece of data is the piece of data you're looking at. But does this make sense to everyone so far?
So if you use the index to go into the set, and then you use and you compare the tags to see
Yes.
if you have a match, and then if you have a match, you use the offset to see which one of the
Yes.
the bytes you select from.
Or you could do the entire, or if it happens to be word size, you could just load the entire word in.
Okay, but if you wanted to get a byte,
Yes. If it were like a specific byte and there were multiple bytes, then you would use the offset to address which byte. But yeah, you're the same.
Are there ways to direct
No. So a direct map means all sets and no ways. Or if you want to think about it, it's one way. There's only one way. And there's multiple sets. In a fully associative cache, there's only one set in multiple ways. Right? If you only have one set, then you have no index bits because you don't need to address that one set. It's always that one set. And important thing I kind of skipped over is that these tag is just the rest of the bits that aren't specified by either your index or offset. You don't need to store in offset because that entire line is in that location. 0, 0, 0, 1, 1, 0, 1, 1 is all in that location. You don't need to specify index because you know that from the set number. Right? If you specify index, then all your ways are going to say set 0, set 0, set 0. It's not necessary to specify something where you indexed into. But you do need the rest of the bits. Because just because I have 0, 0, 0, 0, and it matches the index, doesn't mean that the tag field is going to match. It could be, for example, the next location up, it could be 2, 0, right? Which will also be in the same index. So it'll be the same set. Right? So you need to match the tag. Yes, sir.
Do you need to know the design of the cache in hardware? Because there was a question in the exam, one of the exams, about design the register for the cache stuff like this.
Shirog is going to look at that question and I'm going to move on. So direct map is faster, it's cheaper, less logic, less power, but it's also not as flexible, right? Because, for example, these two map to the same index, and if I use both of them a lot, they're going to kick one, for example, if I oscillate between these two addresses, they're going to kick each other out constantly, and I'm going to lose all benefit from my cache. So it might be smart to combine the advantages of both caches, right? So that's what we call set associative. So
Just to quickly answer this question, that is technically fair game. You may need to know how to implement the cache. There's a question, I'm for somebody who's seen it. That's fair game.
Implement the cache.
Implementing like the exact registers you need, how you do the addressing, how do you change the LC3 to support a cache, all that.
Would you have like
Which
cache
was
hardware?
2006, 2006.
Question 4 in 2006.
We can look at it after. So it turns out that most caches are designed to be set associative. At least some caches in the architecture will be set associative. That means we kind of get the advantages of both. We have ways which the hardware can decide. The hardware can choose what to kick out and what not to kick out. And we have sets where it's mapped by a number, which is easy to access, but the hardware gets no flexibility of how to kick it out. So, to be more explicit, caches will have a valid bit. So every single line will have a valid bit. It will have a tag, and then it will have its data. And often I'm going to extrapolate on this example, and there's more metadata, but this is the basic data you need. So your tag will tell you whether this location is actually the memory address you're looking for, and your valid bit will tell you if this line is valid at all, because when you, like for example, if you just start your machine, there's going to be garbage data in your cache, and you don't want to take that garbage data as soon as it's valid, right? And then you obviously need your actual data. If you have multiple ways, you also usually need replacement bits. Because you need to keep state on how to replace a line when another line comes in. For example, we've talked about least recently used a lot. If way 0 has the least recently used, the hardware can make the assumption that if it hasn't been used in a long time, it's not going to be used in the near future. So it might decide to replace this line. And it might know that the other line is more recently used and assumes that you might use it in the near future and not want to replace that line. So you usually need to keep some statements for replacing. This is not always true. For example, you could take a random replacement policy, in which case you just randomly pick one and you don't need state at all. Right? So that's super cheap, but it might not perform very well. Does that make sense? In addition to the metadata I talked about for a line, let's look at a line more closely. So there's valid. There's valid, tag, and data. Can someone tell me what happens when you kick? When let's say your cache set is full, and you need to replace one line with another line. What happens to the line that you're kicking out, evicting? Yes. So there is a chance that we could have stored to that line. And if we did store to that line, we need to make sure the memory has the right copy of the line, right? Because if we just kicked it out, we would just lose the data we just modified. And that means none of our stores will do it. Right? So we need to update memory when you're kicking something out. And as he said back there, that we don't always have to write back to memory. Because if we didn't store against the line and we only did loads against the line, then the line might not have changed. And we don't really want to put something out on the memory bus, incur all that latency, and use up part of the memory bus bandwidth to do something that essentially is abnormal. Right? Well, we would write the same data back to the same location where it was before and change nothing. Right? So optimization could be that I store, this is called a dirty bit or sometimes called a modified bit, in the cache line to say, hey, I've written to this cache line, or I have not written to this cache line. And based on that, whether it's dirty or not, you can make you can decide to write it back. So if it's not dirty or if it's clean, then you might not bother to write it back. And also in this cache, we could have bits for like permissions, like read, write, execute. We do not need a no MSI protocol insofar as coherency. You can imagine MSI protocol in the same way that I just described, that it's modified or not, it's clean or it's invalid. But that's all you need to know. You don't need to know how it affects coherency or anything. That's all. We have not talked about that. We'll talk about that. Does it make sense? Does anyone else have any questions about caches? Because I believe that is all.
So is it case that they mentioned is like when you want to do like an STB, you first go read from memory and then you store or you modify and then you store it. Like when you do that, how do you do that?
Okay. That's actually a great question. I guess I did skip some stuff about caches. So let's keep talking about caches. So we usually imagine our memory hierarchy like this. Draw memory really big because it's huge. Okay. When we bring something into the cache, we always have a choice, right? If we read something that we know that we never will read to again, so sometimes referred to like streaming data, right? If we read something that like we'll never touch again, then we might not want to cache it. If we write something that we might not ever want to write again, we might not want to cache it. So there are deeper questions about cache design, but basically what you referred to was a concept called write allocate. There's write no allocate, but you also could be no allocate. So the question is, if I do a store against the line, do I bring it into the cache, right? And if I do a store against the cache line, and I do want to bring in the cache, so basically what I'm saying is I'm not writing directly into memory. So if I write directly into memory, that would be called write through. And if I don't write directly into memory, I only write into my cache, that's called write back. So most caches we talk about are write allocate and write back. That means we allocate some space in the cache when we do a store for that location we're storing, and then we don't write it to memory, but we wait until we kick it out to write it back to memory. So that's write back and write allocate. The reason we do this is it's more performant, right? We don't need to communicate to the memory unnecessarily. But this poses a problem. So if I have a cache line that has data that's 4 bytes of data, right? And say, for example, that these are characters or something. So each location is actually a byte. And I decide to change one of the letters in my string or something. So I do a store against that. If I have a write allocate cache and that write back, that's also write back, then that means this is now going to be in my cache. Does that make sense? That means what? What are in the other 3 locations? What should they be?
The same as before?
They should be what memory says it is right now, right?
Yeah.
But if they weren't already in the cache, how do I know what is in memory right now? I have to do a read from memory, right? So intrinsically, if you have a write allocate and write back cache on a store, you need to do a read from memory, which is kind of counterintuitive, but you can imagine that like I don't necessarily write the whole cache line on a store. If I did, I wouldn't need to bring it from memory, right? Because I've changed everything about that line, so I don't care about the original state. But if I didn't store against the entire line, that means I might care about what were the other bits that are already in there. So generally speaking, if you do a store to a memory location that's not in your cache, you actually have to read memory and bring that cache line. Does that make sense? And another thing that you can also think about is whether, since we have multi-levels of cache hierarchy, we know that memory contains everything. We also know that caches only contain part of memory. But if you have multiple levels of cache, you can also think of inclusivity. And that refers to whether L2 contains everything L1 does. Like if it's a superset of L1. And we'll talk about later in coherency why that would be a good idea. Right now it sounds like kind of a bad idea, right? Why would you keep the same copy of things twice? But we'll talk about it in coherency why inclusivity was actually a good idea. But yeah. So you can be inclusive or non-inclusive, or inclusive or exclusive. Where inclusive means that L2 contains everything in L1, and exclusive means L2 does not necessarily contain everything. Does that make sense? Rob prefers the term inclusive and not inclusive. Some people call that exclusive. Computer architects argue about terms constantly. So if you're confused about exam, ask. Does someone have a question? Yes, sir.
Could you explain about the types of misses?
Yes, you might need to know the types of misses. Okay, that's a good question. I forgot that was a thing. So there's a miss called a compulsory miss. I'm gonna have to spell. Whatever. There's conflict misses, and then there's capacity misses. So these are three types of misses. Compulsory refers to the fact that there is no way you can avoid the miss, and this happens on the first axis of the piece of data, right? If I've never accessed, let's say, hex 3000 before, then there's no way I can get around the fact that I'm going to miss in the cache. And the miss here refers to the fact that the data is not in the cache and I need to go to them, right? There's no way that I can hit the cache, which refers to the fact that the data is already in the cache. Because I've never accessed it before, so how would it already be in my cache? So that's a compulsory miss. A conflict miss refers to the fact that two addresses are going to map to the same location in the cache, or at least the same set of locations. So if I have a set with multiple ways, there might be multiple cache lines that could fit in that set. But conflict refers to the fact that two addresses are fighting for a location in the same set, right? And capacity miss refers to the fact that my cache is simply not big enough. So if I'm reading, let's say, if I'm constantly working with a set of data that's 16 kilobytes and my cache is only 8 kilobytes big, then I'm going to incur some misses, not due to how I designed my cache, but simply because my cache is not big enough, right? Right. A conflict refers to the fact that it's not quite that my cache is not big enough, but my set is not associated enough. So if my set 0 has, let's say, hex in our earlier example, these would map to the same set, and then this would also map to the same set. So if I'm constantly reading these three locations, and I'll have two ways, and they map to the same set, that means these three locations addresses are fighting for the same two locations. And so they're going to conflict each other all the time, and one will kick another out, and you're going to incur some misses due to the fact that they all map to the same set. But there's not enough space in that set. A capacity miss, on the other hand, refers to the fact that there's not enough capacity in the entire cache. So a good way to tell the difference between this is, if you turn your cache into a fully associative cache, is there any way you could have avoided that miss? So, because a conflict miss refers to the fact that your set is not associated. If I turn the set one locations into ways instead of another set, then maybe I could have avoided that miss. And if that's true, then that's a conflict miss. If that's not true, and I simply don't have enough space in my cache, that's a capacity miss. And those two are kind of hard to distinguish between sometimes. And what I gave you is a pretty good rule of thumb, but we won't talk about that very extensively in this class. Dr. Chu doesn't really like thinking about these in Sure.
Can you go over what can make data invalid? Is it only when you haven't, like, when you first start running like your computer or whatever, you haven't put anything in there?
So that's a very interesting question that we'll talk about later when we talk about coherence. But as far as you're concerned right now, there's no way to make data. There's no way to make a cache line invalid. The cache line starts off invalid because there's nothing in it, and then as you load a location, load an address, cache line into that location, that's going to make it valid, and you might kick that cache line out in favor of another cache line, but that will still keep the cache line, or that will keep the location of the cache valid because you're just replacing with another piece of data which is also valid. As far as you're concerned, there's no reason something will leave the cache and just leave that slot empty. We'll talk about it later why this might happen, but for now, like if a cache line is invalid, this means nothing was stored in it, ever, since the machine moved.
Can you give an example of a capacity miss?
Sure. So in this example, I have 3 locations, 3 addresses fighting for 2 locations, right? So let's say I have actually 5 addresses fighting for these 2 locations. So I believe those all map to the same set. Let's say they all map to the same set. This is a conflict miss right now because there are the fact that if I only have 4 things, then it's a conflict miss. There are 4 things fighting for 2 locations, but technically there's more space in the cache. I just can't use it because they're mapped to different things. However, if they were fully associative, and I had a cache that only had 1 set, that means this might be hex 0, 2 0, hex 6 0, or hex 4 0. Right? Now at this point, there are no conflicts because I've made it fully associative and everything fits fine. But if I bring in this address now into it, now I no longer have enough space in my cache. And this is not because I don't have enough weights in my cache. This is not because there's a conflict on the way the sets are mapped. This is simply because my cache is only 4 locations and I'm trying to store 5 things in. Right? It's simply not big enough. This is a capacity miss. Yes, sir.
So do capacity misses only happen because only happen with fully associative caches? You have a not fully associative cache that also has a capacity, I don't know whatever you call it, capacity miss or
You can have a set associative cache that will miss because not enough capacity. But the way you differentiate between a conflict miss, if it's 2 things fighting for the same location or it's just not enough space in the cache, is if you redesign your cache, turn it into a fully associative cache, and that address sequence will still cause that miss. If it will still cause the miss, even if it's fully associative, then that miss must have been a capacity miss.
So you said in that case when you're trying to bring in 8-0, it's a capacity, but isn't it the first time you're trying to access 8-0? So would that be compulsory?
That is true. I'm assuming that this is in a. That's a good
does
question.
compulsory take precedence over?
Yeah, sure. If there's no way, like, if I've never seen this address before, there's no way that, like, it could have been in my cache. Anyways, any other questions? Yes.
Could you do 3D and Spring 2005?
Maybe. We could try it. So it turns out we're not actually that great on solving these problems on the spot. People assume that like we're infinite geniuses, but it's not always the case. Doug is pretty smart. Spring what?
Spring 2005.
Spring 2005? Which question?
3D.
3D?
Yeah.
Oh, this we saw this question as one of the suggestions, and this is if like I went through the pain of actually solving this out, I'm sure I would have made a mistake. But so the way you go about solving this problem is you read from the end, because you don't care about anything in the beginning if it gets replaced. So you read from the end and find, for example, four-way set associative is easy, right? Because if it, I believe the axes go from left to right, top to bottom. So these are in the last four locations you access. And in a four-way set associative cache in an LRU scheme, that those will be the four locations that end up in your cache, right? Does that make sense? Because everything else older than that will get replaced because of these four axes.
What do those for if that is not order?
Order does not matter between ways.
But you have to know the offset. Because it's 4 word.
Oh, I'm
It's
sorry.
4 word.
These are. Okay,
So
you
it's
are
2 to
right.
the 2, so there's 2 offsets.
So what?
So you always look for the last one.
Yes. If they end up on the same word, then they're effectively the same address. So you look for the last four unique addresses, right? And same with like set associative. You find the last four unique addresses that map. Well, you find the last two unique set addresses that map to set 0, and you find the other last two addresses that map to set 1. And then for the direct map, you find the last unique one that map to set 0, 1, 2, and 3. Does that make sense? Yes, sir.
Over spring 2006
Spring 2006.
number 2, which number 2?
Spring 2006.
We were actually doing
Yeah, we were gonna do that whole thing.
Now we're gonna do this one. We're just gonna go through the whole question. So caches show which bits of a 16-bit address are used for the set index, address tag, and cache line offset in the 32 KB two-way set associative cache, the 4-byte cache line. Okay. We had 16-bit address. It would be better if you guys see this or the question. Question? This one is not very difficult to. Okay. Okay. So show which question saying you're trying to figure out basically which bits are assigned in the addresses. You have 16-bit addresses, and it says the cache lines are 4 bytes each, and it's two-way set associative. So you're trying to find set index, address tag, and cache line offset. If you have, well, given that information, what would the, how many bits would you need for the cache line offset? You have 4 bytes, you need 2 bits to address that. And then we have the index bits right after that. So index bits is a little bit more interesting. We have a two-way set associative cache, and it's 32 KB. So that means we have 16K per way. So if you look vertically, it's 16 kilobytes. And then within that 16 kilobytes, there's 4-byte cache lines. So the number of cache lines in one way is 16 KB over 4, which is 4 KB. And that's, to get 4 KB different sets, you need 12 bits for the set index. So you have 2 bits for the index, 12 bits for the, 2 bits for the offset, 12 bits for the index. That gives us 2 bits remaining for the tag. So that's just a simple computation. Okay, pardon me. Did everyone get that? that's just looking at the basically the dimensions of the cache and figuring out like what you know. Okay. So then the next question, you have a 4-cache cache line, and each cache line is 1 byte, and it's byte addressable. So you're trying to give a sequence of addresses that give you a 50% hit rate asymptotically. Yeah, I'll get to that in a second. For a direct map cache, a 2-way set associative cache, and perfect LE replacement. With fully associative. And you're trying to use the minimum number of addresses. So first of all, let's talk about the asymptotic 50%. What that means basically, it needs to be 50%. But if you have like, let's say the first time around you have maybe like 6 misses, and then it becomes so 6 misses out of 8, then it becomes 4 out of 8 for the rest of them, then that's still considered asymptotically 50%. So the little jitter in the beginning is irrelevant. It also says use the minimum number of addresses that you can. So let's ignore that for now and see like if we can even come up with patterns that just are not necessarily the minimum. So for direct mapped, we're trying to get 50% hit rate, and we have 1 byte cache lines, and then we have byte addressable. So we know compulsory misses are going to be like they're compulsory, so you have to miss them, right? So the first time around, we're going to miss probably 4 times. We'll need to basically bring in the cache lines to fill up the cache. Yeah.
Do you have to use every single block?
Yeah. So if you looked at the solution, it uses every single block, and I don't think you need to. We won't do it with. Yeah. Is that what you were confused about?
Yeah.
Okay. Okay. Yeah.
Does the same sequence need to give a 50% hit rate for all 3 schemes?
No. It's a different sequence per thing. Oh, and I should also say this is like an infinite loop. You basically do this stream of accesses infinitely. And it's different per thing. So direct map, let's just talk about one set. If we want a 50% hit rate, that means we need, like, we'll have our compulsory miss the first time around. But ignoring that, let's say we have something in the cache. We want to hit in there, and then we want to miss 1 time. So how do you make something miss if it's already sitting in the cache? You have to evict it. Right, so what we need is essentially 2 addresses. We need, they both map to the same set, and basically you read one address, and then you bring in the other one. You read that address, then you read it again, then you bring in something, and then read that again. And what that gives us is the first time you read, let's call it address A. The first time you read address A, it's going to be a miss. Second time, it'll be a hit. Then the third time you're reading address B, that'll be a miss, and it kicks out A. Then you read address B again, that's a hit. And then you do this loop again. So now you're accessing A, which means A is going to be gone because B kicked it out. And so you get this alternating pattern of hitting and missing, and you get 50%. So some addresses that might work with that is like hex 0, and then hex 1000. Or sorry, hex 0, then hex 0 again, then hex 1000, and then hex 1000. And if you do this in the loop, you'll miss 0 and 1000 each time you go through the loop the first time, but then the second access you'll hit it because you literally just read it. Okay, so is any questions on direct mapped? Yeah.
I actually think it wanted 1 for both schemes.
The solution does say both. It's pretty much the same thing. You just have to do the same pattern on a different set. Yeah. So you just like duplicate the number of things. I'm actually gonna start right here. Okay. So direct mapped.
It's not.
It didn't switch.
That's direct map. And if you go back and do this again and again, then it'll basically you'll get that 50% hit rate. So now we have 2-way set associative. Okay, and we'll do the same sort of thing. We'll ignore the we'll ignore the parts where it says minimize addresses and just think about how we can get this to fail. If we do the same thing, so you'd access 0, then hit 0, then 1000, 1000. And the difference here is now this 1000 is not going to kick out the 0 because it's mapping to the same set and there's two ways in there. So this will go in the second way. So you need to go and extend this and say, let's kick out 0 because it's perfect LRU. And then we'll go kick out the other guy. And if we do this pattern, we'll have a miss, a hit, a miss, a hit, a miss, hit, miss, hit. The first time around it's 50%. These are all in the same set. And then when you go back to 0 in the next iteration, then the 2000 will have kicked that location out. And so this will be a miss, then a hit, and a miss, and a hit, because this will be kicked out by the 2000, so on and so forth. And then I'll give you the solution, but that's not necessarily the only way of doing it. So, yeah, I'm saying this is like the naive approach. If you're just assuming you don't need to. Okay, so you brought up a good question. Why do you need 4 of these? What you can do is arrange your hits and misses so that basically one of them, well, you don't necessarily need to kick out both of them. You can abuse LRU so that it works to your advantage. No way of doing that, we'll still need to do this thing. We'll still need to bring that in. Instead of bringing it out, bringing in or reading this again immediately, we'll do that. And then we'll bring in, we'll read this again. That sets that to the LRU. And then, if you do this, you go ahead and replace this hex 1000. And so now, now when you go back, this 0, so when you go back, basically the first time around, this will be a miss, this will be a miss, this will be a hit, this will be a miss. Then when you go back around, you kicked out the 1000 with this because of how LRU works. You instead of kicking out the 0, you put the 0 access here, which means this is the LRU, the 2000 goes and kicks that out. And so this 0 just sits in way 0. This is in way 1. Sorry, this is in way 1. You go back, so this is going to be a hit, and this is going to be a hit. When you try accessing this, the LRU is 2000 from the previous iteration, so it kicks out the 2000. And so what you're doing essentially is the way in which 0 is stored is just always going to stay that way. And these 1000, the 1000 and 2000 are going to be basically hitting in the same, or they're going to be trying to go to the same way. And so they'll keep replacing one another. So you end up with a hit here, and a miss here, and a hit here, and a miss here. And that's after the first iteration. So this is when the asymptotic 50% plays a role. So we got it in three separate addresses instead of the 4. And we also reduced the pattern down to 4 accesses instead of 8. Yeah.
So this has a minimum number of addresses. Does that mean we also have to make the address in this sequence? Or?
No. If you can do 3 with a longer sequence, that'd be fine.
So is it just what you do for the 4 address and just don't use the last address? Yeah, that's fine.
Yeah. If it's 3 addresses, obviously within reason. You could make a sequence that's 1,000 addresses that achieves the same purpose as this, but you probably wouldn't do that. You shouldn't do that.
I think what he means is that in the first attempt that you did with the 4 addresses, if you don't use 3000, it'll still work.
Because you replace it.
That would work. Okay. But we overthought the question then. Yeah, okay, so what they're saying is like you just don't use this 2000. Then the 2000 will go replace this, and then the 1000 will go and replace the. Actually, then the 1000 will be it. And then
So
2000.
0, 1, and 2000. 2000 will replace 0.
Yeah.
0 will replace 1.
Yeah, you're right. But that would mean both of these are hits, right? It wouldn't. Oh, the zero.
The zero would
Yeah, zero replace. Yeah, you're right. Yeah, okay, you're right. So you could do that. This would minimize the actual individual risks. I guess that was a fun exercise then. But yeah, not necessarily. You don't necessarily need to do that. Then we also have four-way set associative. Or fully associative in this case. We only have four ways. And you can do something similar. I'm going to use this technique, but we could do as well. If you have four ways, then you need to have at least 5 unique addresses. Otherwise, since it's 4 ways, it would map to the same thing and don't fit. So you need at least 5 addresses. And I guess just using 5 addresses. Basically, if you do that down to 5,000, if you do that down to 5,000, you get the same effect because the LRU essentially would look like this. So you have 4 ways. So I'll just put the high bit. This will initially have 0, 1, 2, 3, and x4 will go here. And then since the LRU is now this guy, then when you try reading 0 again, it'll overwrite this, and the LRU kind of keeps moving along like this, and you get essentially the 50% hit rate since you just duplicate the addresses.
It's fully associated. Why can't x0 and x1000 both fit in the same set?
You can fit if you go. So I didn't draw all of them. You go from 0 to 1,000 to 2,000 to 3,000 to 4,000, and so you have 5 different blocks, and you can't fit 5.
So that's not the least address.
You need to have at least 5 because you need to kick out. Yeah, you have to have at least 5. Otherwise, you won't be kicking out anything. You could just fit all the blocks.
So let's go to 0, 0, 1,000, 1,000, 2,000, 2,000, all that.
Yeah, and then we could construct basically an example like this, where we actually reduce the number of accesses. But the question's asking to reduce the number of addresses, in which case this will be fine. Okay, so let's do the other one just to see. So what we would do, if we want to minimize the accesses, is 0, then 1,000, 2,000, 0. I believe this works as well. So it's 0, then this, and this, and this, and then you go back to 0, and you go back to this. So your LRU is now 2,000, the 4,000 kicks that out. And then when you go and go back here to 0, you'll have a hit and a hit. So these 2 ways will always hit, and these 2 ways will always miss. So we have, in our ways, we have 0, 1, 2, 3 initially. And our LRU is here, and that's our MIU. Then we go and access 0, go and access 1. So these 2 are no longer LRU. The 2 is the LRU. we replace this with the 4,000, and then we go and we loop back. So we access 0, that'd be a hit. 1,000 would be a hit. 2,000 would now be a miss, but the LRU is this guy. So 2,000 will come here and kick the 3,000 out. And then we go and access these two. And so these become, this becomes the LRU. Oh, sorry, we go and do, first we do 3,000. So we kicked out,
Isn't 4 gonna kick 0?
it doesn't kick out 0 because it's no longer the LRU.
Oh, 4 there. Okay.
Because of this.
That's like
So we re-access 2,000, which kicks out this. 3,000, which would actually kick out
4.
no, it would kick out the 4. The 4,000 the LRU, and then the 4,000 would come in. We access these two, making this guy the LRU. And essentially, what we've done is we've reduced the LRU to these two last ways, and these two always hit. And so we have a hit, miss, miss, hit, miss.
But
That's not 50%.
Yeah.
Yeah, you're right.
until you get 50%.
Okay. Yeah, I think you would actually have to have another address. Okay, well,
Don't you have to compare the first axis, like the first 4 axis?
what do you mean the first
Like
four?
the first iteration.
Yeah, the first iteration you can kind of ignore since it's asymptotic time. Yeah.
Think,
This one.
think steady state.
Yeah. And after the first axis, you'll have like this sort of pattern because these are just going to sit there in way 0 and 1. So you have to have one more miss here. Yeah. In that case, you'd actually need another address. So it turns out this reduces the number of. Yeah. Okay. So this would be 10 different accesses. This is 8 accesses, but then this would be an extra address. So, long story short, this was actually the correct solution, where you just do 0, 1,000, 2,000, 3,000, 4,000, and then 5,000. Or sorry, just 0 to 4,000. And you just the LRU just kind of moves along, and that's kind of a contrived worst case for LRU. In fact, you can just draw that out. It's a good exercise. So 0, 1, 2. So if you have these accesses, and you have 4 ways, and they all map to the same way, this is the worst case for LRU, because actually everything would always miss. 0 would miss, then this would miss, then this would miss, then this would miss. Then 4,000 goes and kicks out 0. So 0 would miss again when you try accessing it, and it would kick out the 1,000, and then 1,000 would miss, so the LRU keeps traveling along. And this is like the worst case for LRU. So there are like, LRU is not the best best replacement to use like in every situation. Which apparently that's what part C asks. Okay. So in part C, we've touched on it now. You have same thing, 4 cache line, 1 byte cache lines, byte addressable, and you try and come up with an address that is better for direct map and terrible for fully associative, and that's LRU. So the case we came up with, 0, 1,000, 2,000, 3,000, 4,000, they all map to the same set, which means LRU is going to shift from, first it'll be the 0, then the LRU will be 1,000, and 0 will go kick that out, and then the LRU will be 2,000, and the 1,000 will go and kick that out. So that's the worst case for LRU, but if it's direct map, well, these addresses would actually also map to the same set. But in direct map, if you have, let's say there's 2 bits for, or there's 0 bits for byte on block, because there's no offset. Index is 2 bits. So we'd have, basically, just have x. Three. So these would all map to different sets because the index bits there's two index bits in locations, bit 0 and 1. These are all different sets, and we'll have that same other one we had, which was hex 4. Well, hex 4 always maps to hex 0. It maps to the same set, so it'll keep kicking out hex 0, and 0 will kick out hex 4. So in our cache, we'll see basically this will have 0, 1, 2, 3, and that'll be kicked out by 4. And then we'll go and hit these guys, and this will be kicked out by 0, and so on and so forth. But with the fully associative, we'd have the LRU moving, and it would always be a miss. Okay, so. Okay, for the they're all going to be misses in the beginning. So the first pass, it'll be this will be a miss. That'll be a miss. That'll be a miss. Will be misses. And to actually see the benefit, you have to do another iteration of this. And so then 0 will be a miss. 1, 2, 3 will be hits, hit, hit. 4 will be a miss. Right? So what you can think of as 3 out of 10 if it's like this, or if you start looking at like infinite loop, which I don't think this question was asking for an infinite loop, but you could basically ignore these, and the hit ratio would always be 3 out of 5 for the direct map. In the if you have an infinite loop. But 3 over 10 is like the minimum where you'll see the benefit, whereas the LRU will just be 0 out of 10, or like 0 out of 5 or whatever. It'll just always be 0. Yeah.
Maybe just use 1, 2, 3, 4.
Yeah.
And also down. What can we do just 1, 2, 3, 4?
For part B,
it has to be 1000. Why 1000?
For part B, it doesn't have to be 1000. You just need to make sure they all map to the same sets. And so if 0, 1, 2, 3,
but
they will map to the same set.
I know 4 is
yeah, so if you could do 0, 4, 8, and 12. Those would all map to the same set.
Yeah.
Yeah, that's the only thing. I used to use 1000 because it's like easier to write. It's easier, like they're definitely on different like addresses, and they're also, if you look at the index bits, on the same set. It's just a little easier. Okay. Yeah. Any more cache questions? Okay. We have a memory one, which. I kind of. Yeah, that's fine. In the long, like the infinite loop, but if you just do the kind of minimum sequence, it'd be 3 out of 10. Either one would be fine. Just clarify what you're saying. For this one,
you probably should ask us what
yeah.
we mean first. And then, if we don't care, then write the answer you think and then clarify it.
Yeah. If you ever have like any sort of doubts on a test, just put an assumption. Well, first ask us, and if like you're still confused, just put an assumption, and we'll try to grade that assumption. Okay.
You guys do you guys want to work this problem?
Look at the actual question. If you go down, it's basically just asking like the index bits. Sorry, where the bits are assigned and how you can improve the performance. It's a memory question.
This is the one with the exam?
No, this
is one of the problem sets of Dr. Pat.
Yeah.
Last year. If not, then we're gonna work a data path question. Would you guys prefer to do that?
Do stuff about the design, those questions of the exam.
Yeah.
Like how to go about those.
So we're gonna do a data path design question. Remember which question it was? like to do the least significant one or the counting instructions one?
Counting.
This one?
This one, because the solution has like, it's not, has approximate.
It has a lot of assumptions.
Assumptions.
About the new map.
So this is the thing about that. Those questions are really hard to see what assumption can we make and what not.
So generally, so you make as few changes as possible, basically.
But like, for example, you said a temporal register D, and D could access, looks like D could access everything. You can pass it to A and B in the LEU.
Yes,
No
so
problem.
it says you can assume the temporary register T can be accessed like any other general purpose register. This means you can imagine that it's in the register file and it has access to like the ALU that's shifted.
But the thing is that because it's 0, then SR2 will not read from. We're always gonna read the immediate. We're not gonna read it as a register. SR2, you see what I said.
You would have
So,
to mux
SR2
SR2
max
or
is
SR1
always gonna read the
choose
immediate. It's not gonna read from the register file. And we don't have access to this R2. We don't have a control to the SR2 max.
Because SR2 is hard coded to IR 2 through 0.
Oh, you're saying
Yes, because
And they don't
the fifth bit
actually
is 0,
mention
so we're
that.
always gonna read the immediate. We're not gonna read from the register file.
sure. And oh,
So you can't
Oh.
add from two registers together.
Yeah, that's true.
So it's really-
yeah. So they should have used the shifter in this problem. They didn't for some reason, but they could. So let's start from the beginning because I'm sure not everyone knows what this question is. Basically, you're implementing an instruction that looks at the bit vector in a register and picks a register with the least significant one. So this means that if the last bit is a 1, bit 0 is a 1, you return bit 0, or put 0 into DR. If the bit 0 was a 0, but bit 1 was a 1, it put 1 in DR, and so on and so forth. So that means it's DR either contains 0 through 15, depending on which is the least significant one, or if the SR is completely 0, it would return 16. Does everyone understand what this instruction is going to do? Because if you did this in a program, it would involve a lot of like instructions of shifting and then ANDing. It would be very slow. So if you implement it in hardware, it might be a lot faster. So that's the general idea. So a couple of things you get to use. Modify the state diagram to support the instruction. You can assume that there are no constraints on the next state. Your modified microsequencer, so you can just, you don't need to worry about state assignment. You get a couple new micro branches. So you can go to a different state depending on branch negative. You can go to different state depending on branch 0 and branch P. And then you can kind of just, so basically this is abstracting some of the like nitty-gritty details of the microsequencer away. But basically you get to choose when you set these negative 0 and P, positive bits. And you can assume they're just like condition codes. So a good assumption for this problem is that this BNZ and BP loads condition codes off the bus like the normal condition codes do. And then in addition to that, you also have a temporary register T, so you can store a temporary value, and then minimize states, no other data path allowed. So if we start off with this premise, does anyone have any ideas of how you go about solving this problem? Like, at a high level, what do we want to do?
Check the least significant bit. It's not one.
Yeah. So we start off with the LS bit B, bit 0, and see if it's 1. And then if it's not, maybe we can check the next bit, bit 1, to see if it's 1. If not, then so on and so forth, right? And so,
You have to count to
yes. So we need a shift. We either need a shift SR or we need a shifting mask that goes from bit 0, 1, 2, 3. And then we also need a value in DR to figure out whether to set a value in DR so that DR eventually will contain what bit is set. So basically, we want to develop a state diagram for this question.
How can I develop set diagram and we don't know hardware how to start? I'm not sure like even what I can use, what I cannot.
So what aren't you clear about what you can and cannot?
It's like for example what I can do with register T.
So you can assume it's in the register file. Let's pull this. Sorry. Sprung is going to be a little harder to visualize. I'm going to pull up the data path. So, as I pull up the data path, so it says that we now have a temporary register T that is accessed like a GPR, a general purpose register, so you can just assume it's in the register file. So that means it can be read out of SR1 or SR2, technically, and then it can access the ALU addition. Does that make sense? So the way you go about this problem is that I'm going to switch to the wrong docket. You can think about this problem like you have a bit vector, right? So it's 16 bits, and this is going to be an SR. And then you want to 15 through 0. You want to progressively check if that is a 0, and if so, then the DR should be equal to 0. Or you mask the next bit, and then DR is going to be equal to 1, and so on to DR equal to 16, right? So you can either think of storing SR in the temporary register, or storing a mask in the temporary register. So you can shift SR or you can shift the mask. And in this solution, they talk about shifting the mask. So that's what we're going to do. So the first thing you want to do is you need to initialize DR and you need to initialize the mask, right? And so, what should go in DR in the first place? What should you initialize DR to? DR. So DR gets 0. And the mask? Sorry? 1. So so the mask is gonna go into T. So we're gonna just put 1 into T. And how do we get 1 into T? Sorry?
The first 5 bits for instruction.
The first,
On the
like
zero
the lower 5 bits. Yeah, we can use the immediate field in theory. So if we could get the immediate field into. There's no pass. This question is kind of strange.
Yeah, I can do it like
Yeah. So we can find other ways to do this. Okay. Let's. The solution is a bit weird. We're gonna find other ways to do this.
can you ask the exam about you have problem with
This,
the design and stuff like
the
this?
exam does not have this problem. It's much more clear, but we're gonna think of different ways to do this, I guess. Yes, sir.
If you go back to that question,
Sure. Sorry, this is gonna be a huge mess because there's just too many pages to show you.
So you have 0, 0, and then 1 for the last 6 bits for the low significant bits. That's like a left shift by 1, right? For the shift register or shift
Sure.
logic.
Sure.
Are you supposed to use that?
You could. You can, if you provide some data into SR1, the output, you could potentially shift the data. Yeah. 0, 0 left. I don't remember. Y'all would know that better than I would.
It's left shift.
Okay. So, well, that's actually really interesting. So you have a left shift built into the instruction. So first, let's think about how to get 1 into the temporary register. So our temporary register presumably lives in the reg file somewhere, and so we want to somehow get the immediate into the temporary register. That's a good question. Does anyone have any ideas?
Can you just use the 0 input to the ALU and XOR it with 1? Because then you just and then the output of ALU would be 1.
The 0? Where would you
So
get
like
a
from
0?
SR, can you get oh never mind, that's one of the outputs to ALU is 0. Okay, never mind.
Your DR already has 0, so you can put it at A and put the immediate value at B and add the 2.
Okay. Then how do you zero out the DR?
Yeah, this.
XOR.
You can't do both in the same. You have to put 2 states at
Sorry?
You have to put 2 different states for one for zeroing out DR.
Right, but how do you...
We cannot use the LEU because bit 5 is 0, set to 0. It's hard coded.
So your problem is how to put 1 into T.
Okay, there was a suggestion from back there that I can get a 1 into T by XORing the 1 immediate field with 0 from the DR. But this assumes that the DR already has a 0 in it. And the question is, how do you get a 0 into D?
Doesn't the instruction have a 1 at the end?
Yes. But we need to find a way to get it into the temporary register, which lives in the reg file. Which means that we have the immediate field, 0 through 4. We need to somehow get it through SRMux. And SRMux, since it takes our bit 0, or 5, which is 0, it's going to take the immediate, and then it's going to go through, it's going to take the immediate and pass it to ALU, the B port. But then we need to figure out how to get B into the bus, onto the bus unchanged. And there is no pass B in the ALU. There's a pass A, but there's no pass B. Okay, that's not a bad idea. So load, you're saying load T through this mux.
Yeah.
So that's actually a great idea. So we know for a fact that bit 5 is a 0. So we could use the 5 to 0 through this mux, don't left shift it, add it to what?
Yeah,
2
this-
point.
Let me change
It's
the
either
button.
PC or source register 2.
Yes.
So, I think the solutions for a lot of these exams kind of play it fast and loose with what
Yeah.
outputs from the register file.
It does
So
seem
can
like
we do that here and just say DR XOR with DR?
You could, but that wouldn't be preferable if there was an actual way to do it. So I'm trying to figure out if there were an actual way to do it.
So in this particular one, we can't edit any of the messages.
No. So this one, you just use the existing state machine, or the existing data type, plus these new conditions, as well as this temporary register key. Yes, sir. So what comes out of that one? Yeah, that's fine. What we're trying to do is get 1 into T. And T is in the register file, and 1 comes from the instruction. So it comes from the IR. So IR immediate only goes through this SR2 mux. Right? It doesn't go, there's no SR1 mux that it goes. So we can get 1 into T by XORing it with 0. But then I don't know where to get it 0. If there's no way to get it.
What about XORing in the destination register with itself?
So the problem is SR2 is currently hard coded to take the immediate. Because that takes the.
So you can assume it's always getting 0, 0, 1. So B is always equal to 1. Always. Yeah, in this design, B is always equal to 1. B in the LAU is always equal to 1. So we cannot use the LAU unless with 1.
Yes. Yes, basically B is always. There's actually something you could do. You could run the shifter so many times until. That's actually interesting. You could pass DR through SR1 and then shift it.
DR, can you pass DR out of SR?
Yeah. The SR1 mux can select the DR. It can select
Yeah.
the
There's
So you
the
have
SR1
16
mux
states.
has 11 through 9. Yeah, and then you can basically burn 16 states and left shift it until there's a 0 in DR. That's a completely absurd situation, but since they don't actually provide a way to get a 0 into DR, I guess that's the best we can have.
What if you left shifted it once and then added it with the last 4 bits and then added it?
Oh, that's actually a lot smarter. So you could. Okay, that is very clever. Okay, let's do that. You guys are doing my job for me. Now I don't need to figure this out. So from back there, the solution was we're gonna use the shifter. Okay, so from if you guys remember the shifting instruction, the shifter, the 2 bits 5 and 4 are both 5 and 4. Either 5 and 4 or 6 or 5 and 4 are both 0. So we're gonna do a left shift. It's hard coded from the instruction. So if we take the shifter and do a left shift, we and how much we're shifting by comes from the last 4 bits. And we know from the instruction that the last 4 bits is a 1. So we could take DR, go through the shifter. We could left shift the DR by 1. And the DR can be passed through the SR1 port using the SR1 mux, if you guys remember from your lab 3. And then we can store this back into DR. So now what we've done is essentially multiplied DR by 2. And this bit 0 is a 0. So this could be our first state. And remember, the goal here is to get a 0 into DR. Okay? And then what we could do is DR. Now DR again is coming out of the SR1 port. We can AND it with 0. 0, 1. So this again comes from the immediate field. And now, since we know the last bit is a 0 in DR, and we know all the other bits are 0 in the immediate, this will be sign extended. It's very absurd, but this is better than my solution. So now DR is going to get cleared. Kind of crazy and convoluted, but it works. Does everyone see that? And this has the effect of dr gets 0. That's all we're doing.
So if we were actually on the test doing this, it would probably be smart to just write a statement that said dr gets
Yeah.
0, right?
It'd be a lot more reasonable on a test to assume there was some way to get 0 into dr. The most reasonable thing to do would be point out to us that like this doesn't make sense, and then like we'll probably make a clarification on that. Occasionally we do make mistakes like this. I assume in that class I either had different assumptions about the data path or there was a clarification during the exam of how to get 0 into dr. But this is how we're going to get to 0 into dr because I'm being pedantic with the data path, and this seems like the simplest way to do it. It's a very good suggestion. What? X01 is the immediate value, and that's where this one comes from as well. They're both from the immediate value. It's because SR2 is hard-coded to 1, basically. Hard-coded to 0, 0, 1. And we can only do what we can with that. And then how do we get 1 into T? Well, also a suggestion from the back is now dr, we know it's 0. Dr is 0. If we XOR dr with, again, 1, the ALU has a XOR, and we can provide it with dr for SR1, and we can provide it with the 1 for the immediate. And so now that will produce what? 1. Exactly. And then assuming T is in the register file, we can load register file. So that's the first 2 states.
Yeah. Why did you choose the XOR not added?
Oh, yes, we could add. I mean, it's the same thing. XORs are cheaper. Because if you look at the data path, 0, 1 is coming out of going into the B port, and there's no pass B in the ALU. You can't just take the B input and pass it through the ALU. There is a pass A, but there is no pass B. So you need to add it to something or do something to the 1 and keep it a 1. And so in this case, we're adding it to 0 or XORing it with 0, same effect. Okay, yeah, add is more easy to think about. 0 plus 1 is 1. So now T. So basically, these 2 states gave us dr gets 0. This state is going to get T, make T equals to 1. So, I'm going to simplify. So, I'm going to simplify now and just have my first state is 0 goes to dr. And my next state is 1 goes to T. Is everyone fine with that? Because that was taking up too much space. Yes, sir?
Just XOR here.
Yes.
So SR2 is decided based on IR size.
Yes.
Whether it is immediate, and that has been set to 0. So it would be using the value from the register, not the immediate value.
Is 0 not? I thought 0 selected immediate.
No, it's not.
Isn't 0 select immediate?
Yeah, one
So now they kind of hardwired to R1.
That actually makes this problem impossible. Huh. But then you can't. Then we don't have our left shift anymore. Yeah, it seems like the problem is broken. There could be a way we maybe could go through gate AR or something, but it's not really instructive to discuss this any further. There's clearly something wrong with this question on the exam. But let's actually finish solving this question. So if this starts off, if this is my mask, I forgot where my problem is. Sorry, I'm gonna pull up the problem again because I don't. Okay. So my dr has 0, my t has 1. So I want to I want to check the last bit right now, right? That's the point of my mask. So what I'm going to do is dr and t, right? So that's going to get me my bit 0. Does that make sense? And then based on this result, I'm just going to load it onto the bus. And since I read condition codes off the bus. Oh, sorry. Sorry. And then, so the question is whether my last bit is a 1 or a 0, right? So either or. So if SR's last bit was a 0 and I mask it with T, I'm going to get all zeros, right? So I can set my B0 condition. Does that make sense? Right. So if my last bit were a 0, then branch on 0 will be true. If my last bit were a 1, then this AND will not generate a 0, and my branch on 0 will be a false. Right? So this just sets the bit. It doesn't actually do the branch. Right? It's like branch enable. You set branch enable and actually branch on branch enable separately. That's actually mentioned in the top. So then what we can do is during this state we either, if the 0 was true, if branch on 0 were true, if branch on 0 were false, that means that the last bit was a 1. That means we found our 1. So this, we can just go to, our instruction's over. We go to 18. It's because dr already has 0. And that's already the right value. Does that make sense? So our bit 0 was a 1. So if branch on 0 was a false, we can just finish the instruction. It's done. If it were true, that means the entire string is a 0. That means the last bit was not a 1. That means we need to do something more interesting. So during this state, we branch 0. We also, this is a good time to shift the mask. So earlier we said we had a left shift by 1. Let's assume we still have a left shift by 1. And we're going to left shift t by 1. And then put that back into t. So now we're moving the mask. Does that make sense? Because I need to mask the next bit out, the next iteration I'm doing this. Does that make sense? You seem confused.
So there's not extra state for the branch takes from that?
I can do stuff during the same state of
Okay.
my branch. That's not actually a problem. What I shouldn't be doing is setting the branch bit and branching during the same state. So I set it in the state before. So I'm actually going to use... There's another question?
Are we allowed to do that branch work based on true or false and the same state that we're setting condition codes?
No. So I separated out the set VZ with the using of VZ.
Don't you need to set CC now?
Yeah, I'm not done with this state. But so another end condition we're also worried about is if we shifted the mask so far that now there is I've shifted out the 1. So basically there is no 1 in the entire bit vector, right? So I could have left shifted this 1 in t so far that there is no longer a 1 in the entire vector. So that means I've never found a 1 in my vector. And that means that my dr should be set to 16. Does that make sense? Right? So I also need to check for that condition. So I'm going to set BZ again. Right? This set BZ doesn't correspond to this true and false. It's going to correspond to the next true and false. Right? So I'm going to have another state. Now it checks whether my vector got shifted out to 0. So if it did, so if it is true, so what happens is this t is setting this branch 0 condition. So if t equals to 0, that means I've shifted so far that there are no 1s in my entire bit vector in SR. So that means if it's true, I'm just going to go back to 18. And then if it's false, then I'm going to loop back. Right? I'm going to loop back to this state and start this process over again. and this I'm branching on Z again because this corresponds to that set VZ. And during this state, I also want to increment dr. And so to do that, I can just add dr. And again, this one comes from the immediate field, assuming we can't use the immediate field, as they seem to assume in this condition. Does this make sense? So this corresponds to two ending conditions. One we found our one already, and one that we shifted so far that none of the 16 bits are one. Does that make sense? Does everyone hopelessly lost or too boring?
Give the assumption.
Yeah. The assumption we're making here is somehow we have a left shift and we're hard coded. That is the only two assumptions we need. Or one assumption we need. Anyways, that is all we have. Does anyone have questions? Yeah, I don't know.